So in the previous example, we considered a two-dimensional vector field, a conservative vector field, and we even found the corresponding scalar potential function. Okay, next, we are going to consider a three-dimensional conservative vector field, and here we are going to calculate the same scalar potential function that corresponds to these three-dimensional vector fields. Okay, so let's consider the third example. So show that the vector fields f, these two vector fields are conservative, and then find the scalar potential function little f such that the vector field f equals to the gradient of f. Okay, now I think in example 13.3.1 we showed that this first vector field is conservative. If it is conservative, we know that there exists a scalar function such that the gradient of that scalar function equals to the given vector field. Now here our goal is to find this little f. Okay, so now if you consider the gradient of this scalar function, you will get something like this: partial f over partial x, partial f over partial y, and partial f over partial c. This equals to the given vector field. The given vector field f is this one, 2xyz, comma x squared c and x squared y. This equals to the gradient of little f. Now using this vector equation, we can construct three equations. So from this we can say that partial f over partial x equals to 2xyz, because that's the first component of the vector field. Okay, let's say this is our equation 1. Then if we consider the second component of the vector field and compare the left hand side and the right hand side, we have partial f over partial y equals to x squared c. That's our equation 2. And finally, from the third component, we have partial f over partial c equals to x squared y. Okay. So basically we know the derivative of f with respect to the x variable, derivative of f with respect to the y variable, and derivative of f with respect to the c variable, and somehow we need to figure out this original little f. Again, the process is very similar to the previous example. So usually I start with equation 1. Let's say equation 1. Then we have partial f over partial x equals to 2xyz. Okay. Now this is the derivative of f with respect to the x variable. So to get f, we have to integrate this one with respect to the x variable. So it's a partial integration. So now little f, which is a function of three variables, equals to the partial integral 2xyz with respect to the x variable. Now if we integrate this, again we have to treat variables y and c as constants. So we have 2 times yc. Integral of x with respect to the x variable is x squared over 2. So we have 2yc x squared over 2. But now we need to add a constant. In general, our function f depends on x, y, and c variables. So if you integrate something with respect to the x variable, maybe now here we should have a function g with the function of y and c. Because in general, if we have a function that contains only the y and c variables and derivative of this one equals to 0 with respect to the x variable, derivative of this one equals to 0. So when we integrate something with respect to the x variable, we should add a function with y and c variables only. Okay, so this is our new f. If you simplify this, you will get f, the current version of f equals to x squared yc plus g of y comma c. Okay, now we need to figure out what this g is. Okay, so far I used equation 1. So to use equation 2, I need an expression for partial f over partial y. Okay, so from the problem, we know that partial f over partial y equals to this. But at the moment, my function f is this. So let's construct an expression for partial f over partial y using the function that we found. So derivative of f with respect to the y variable equals to, so we have to treat x and c as constants. So x squared c, derivative of y is 1, plus, now derivative of g with respect to the y variable is partial g over partial y. And I use the partial notation because y is a function of y and c. Okay, so this is the equation that we found for partial f over partial y. Let's say this is my equation 4. Okay, now let's compare equation 4 and equation 2. Equation 2 says partial f of partial y equals to x squared c. But equation 4 says partial f of partial y equals to x squared c plus partial g over partial y. Now this means, if you simplify this, this says partial g over partial y equals to 0. But remember, this g is a function of y and c. So if you integrate both sides with respect to the y variable, okay, you will get g of yc integral of 0 with respect to the y variable. This equals to integral of 0 is 0 plus, but in general we can have a function of, now we can have a function of c variable only. Because if we have a function that only depends on the c variable, its derivative with respect to the y variable is 0. So you will get this equation. Okay, now let's update our function f. So first we thought that f equals to x squared yc plus g of yc, but now we know that g of yc equals to a function that depends only on the c variable. So now my f equals to x squared yc plus some function h of c. h of c. Okay. Okay. Okay, now let's see. So we have used equation 1 and equation 2. So next we want to use this third equation. To use this information, we need an expression for partial f of partial c. Okay, so using this equation, let's construct an expression for partial f of partial c. You will get x squared y plus h, so let's say dh over dc. This is my equation number 5. Now what we can do is we can compare equations 3 and 5, because both the equations give an expression for partial f of partial c. Third equation says partial f of partial c equals to x squared y, but our equation says partial f of partial c equals to x squared y plus dh over dc. Now from this, if you simplify this, you will get derivative of h with respect to the c variable equals to 0. Okay, now let's solve for h. To find h, we want to integrate both sides with respect to the c variable. Okay, integral of 0 is 0. But now we need to add a constant, because at this point we know that h is not a function of c. So we just need to add a constant c equals to h of c. Now let's update our function f. Okay, yes, so let's consider this one. Our little f. So finally we have an expression for f. And what is our f? Our little f equals to x squared yc plus some constant. So this is our little f. Of course, we do not know how to calculate this c value, this c constant, but this is the general solution for this for the conservative vector field.